After a recent breakthrough in nuclear fusion research and what the U.S. Department of Energy had called one of the most impressive scientific feats of the 21st century. Of course, that's debatable, but we thought we'd break it down for you this morning using an experiment. So Dr. Scott Holmstrom is a physics professor and the department chair at the University of Tulsa. He's here to help us out this morning. Good morning, Dr. Holmstrom.
Thanks for having me, Dave.
So obviously, we know we already have nuclear power plants out there now. What is the difference between what's being discussed now with nuclear fusion and the existing nuclear power that we already have?
Okay, so existing nuclear power plants use fission, which is taking the big molecules like uranium-235, which has 92 protons and 143 neutrons, all in the nucleus of the uranium atom. And they break it in half, and that releases energy. The problem with that, it works very well, and we can control it, and it happens sort of spontaneously. It's easy to get that reaction going. The problem with it is the byproducts are hazardous materials and need to be sequestered from human society. You need to bury them deep in the ground. Okay, so fusion, on the other hand, takes the small molecules like hydrogen that are readily abundant on the Earth's crust in the oceans, and takes those hydrogen nuclei and gets them close enough together so that they fuse into one nucleus. And the recent experiments were two hydrogen nucleus fusing together to form a helium, and that releases energy. So the byproduct of it is
helium.
Helium, which we fill our kids' balloons with, and you know, we're in short supply of helium.
Not toxic waste that you have to like bury in the ground. And so endless source of energy, I keep hearing this term being bounced around. This could be an endless source of energy, endless source of energy. What does that mean?
The oceans are full of water. Water has two hydrogen molecules. Okay, so we can talk about fueling all the energy needs around the world with essentially an Olympic-sized swimming pool full of hydrogen. So
my goodness.
That's what they mean by endless supply.
You brought a wonderful experiment here, Dr. Holmstrom. Tell us how this is going to help demonstrate one of the challenges that they had to overcome with this.
This is the challenge of fusion, is that when you're going to try to put two nuclei together, you got to get them really, really close, basically touching. And in order for the strong nuclear force to take over, that's what holds nuclei together. Okay? The problem with that is both nuclei have positive charges, which we're kind of familiar with in our everyday life about electrostatic charge.
Yeah.
Most of the time it's about like our socks sticking to our sweaters when we pull them out of the laundry.
Right.
Okay.
Right.
But so the real challenge is they're positively charged, they're like charges, so they repel each other, and the closer you get them, the more they repel. So that's the real challenge, and I got a little demonstration that we usually see this electrostatic attraction, but we don't in our everyday lives see repulsion. Okay, so
here we go. This is part of the experiment.
Yep, just got to get this blown up. This is a regular balloon. Branded TU. No, it's not the TU. Okay, so
we've got them.
It generally is just a regular balloon, but if you rub two dissimilar materials together, in this case a balloon and my shirt, you can transfer electrons between them.
Right.
Like in this case, electrons are moving from my shirt to the balloon. The same way as when you walk on the floor, you transfer electrons from the floor to you, and you get close to a yes. Yep.
Yeah.
So that happens in our everyday life. So this becomes charged, and that's electrostatic attraction.
Yeah, exactly.
Okay.
You know, here we go. Perfect. All right.
Now,
what I want nuclear fusion. Okay, what's the next problem?
Right. So,
no, I'm good.
Yeah. So that's attraction. So to get to show repulsion, we need to have a little bit of a sophisticated material. This is just like aluminum foil you'd have in your house, but it's really thin.
Okay.
It allows it to float. It would fall under gravity, but very slowly.
This is going to be cool.
What I'm going to do is you keep holding on to that balloon. I'm going to need you. So this is just a PVC pipe.
Just plastic.
Yeah, plastic. I'm going to charge it up so that now the wand and the ring have the same charge, so they repel each other.
You're moving it with the repelling forces on the plastic.
Okay, so now I want you to hold the balloon under it.
Okay. Wow.
Okay, so if you were going to let's pretend these are two nuclei.
This is literally like magic, doctor. This is amazing.
So if these are two nuclei, can you propose a way? Yeah, see, when you try to move it closer, it moves away. Right, so how can you do it?
Tell me.
Let's bring it over here. Move it real fast.
Oh, I got to move it real fast. This
hold on.
Awesome. We're going to do it one more time. We have a little bit of time. Here we go. So what do I need to do?
Just move it as fast as you can.
Kiss it.
There we go.
There we go.
So every time, so that's what the lasers and the capsule at the Lawrence Livermore Labs, that's what it was doing, was taking these two protons and forcing them together. And when you use more energy, when you use less energy to force them together than you get out of the fusion reaction, that's called ignition.
And they said
that's what
net
they did.
Gain energy, which was a big thing.
Right.
Wow, Dr. Holmstrom, thank you so much. I hope this was enlightening for you at home as it was for me. Very interesting, and all the best as they continue this research. Thank you so much.
I appreciate it.
Boats, RVs, and other outdoor things, many items coming to the Cox Business Convention Center this weekend. After the break, what people can expect at the Oklahoma Boat Expo as it comes back to Tulsa.